Welcome to Ask and Learn.
We are going to prove Fermat's theorem for the case in which the function f has a local minimum at C. So we know that in the text book it was proved the theorem for the case in which the function has a local maximum. And we got to remember that the theorem says that if the function has a derivative at the point where it has a local maximum, then this derivative is zero. So we want to prove that if f has local minimum at C, then its derivative at that point, if it exists, is zero. But for this, we're going to use exercise 78, which says that if a function f has a local minimum at a point C, then g of x defined as negative f of x has local maximum value at C, at the same point. So here we're in that case because we are supposing that f has a local minimum at C. That's the hypothesis for the exercise 78. So theoretically, from exercise 78, we know that the function g of x defined as negative f of x has a local maximum at C. Okay, so now because this function has a local maximum at C, we can apply the part of the Fermat theorem that was proved in the textbook. That is, the case of a local maximum at a point. And we know the function g has a local maximum at a point C. So, using the part of the theorem proof in the text, we know that g derivative at C is zero if it exists. So if the function has a derivative, the function g has derivative at C, we know that f also has derivative at C because we know that g is negative f, so the only difference is a sign. So differentiability of one of the functions implies the differentiability of the other, and moreover than that, we know that the derivative of f is equal to negative the derivative of g at x for any x, because this function here, we can put the negative sign to the left of the equation, and f is then equal to negative g, and the derivative of f is then equal to negative derivative of g. But this equation holds at C. That is, the derivative of f at C is negative derivative of g at C, but this is zero because of this. And this implies that the derivative of f at c is 0, so we have proved the theorem. Theorem has been proved. For the case of a function f that has a local minimum, the idea was using what was proved in the textbook, that is the case for the local maximum at c, and the exercise 78 that says that if the function has local minimum at a point, then negative that function, this new function defined as negative, the given function has a local maximum at that value. Using then the theorem, the part of the theorem that was proved in the textbook, we conclude that the derivative of the given function at c is 0, and then this is the proof of the theorem in the case of a local minimum at a point c.